What is new about exercise 3 is that instead of comparing a mean to a number, we compare a mean to another mean. It is believed that employees who occupy directive positions sleep on average fewer hours a day than employees in regular positions. A random sample of 11 employees in directive positions and 20 employees in regular positions is selected in the county. The following table shows the summary of the collected data. In directive positions, the sample mean is 6.8 hours with a standard deviation of 1.2. In regular positions, the sample mean is 7.5 hours with a standard deviation of 0.9. Obviously, this sample suggests that those in directive positions sleep less than those in regular positions. But how strong is this suggestion? Could these two samples come from two populations with the same mean? Letter A. Use the appropriate hypothesis test to get a conclusion about the matter. As always, the first step is setting up the hypothesis. The null is the equality. The mean among directive positions equals the mean among regular positions. And the alternative is the suspected inequality. The mean among directive positions is less than the mean among regular positions. But to do our math, we need to compare to a number. So we express this equality in this form and this other equality in this other form. Second stage, selecting the appropriate mathematical model. These samples are not big enough, so our model will be valid only if the population distribution of hours of sleep a day is normal. Here we should do something to check normality. The simplest thing that we could do if we have the whole data set, this is just a summary, is sketching the dot plot of each sample. If the dot plots look bell-shaped, it might be a symptom that the population is normal. If they look skewed, it might be a symptom of the contrary. Of course, doing this is not very reliable because how much of a shape can we see in samples of size 10, 11 or 20? Oftentimes, not too much. Anyway, we can always run the test and at the end point that the results are to be taken with a grain of salt because the samples are too small and normality is not guaranteed. The mathematical model here is similar to that which we saw in Chapter 7. The sampling distribution of the difference between the two sample means will follow a normal model whose mean is the difference between the population means and whose standard error is given by this formula. This formula is easy to remember if you understand it in this way. This fraction is the variance of the distribution of this statistic. This other fraction is the variance of the distribution of this other statistic. And the variance of the difference between both statistics is the addition of their variances. The variance of the difference between two variables always equals the addition of their variances if the two variables are independent. To apply this mathematical model, we require the two samples to be independent. Here they are. In the next exercise, we will see what to do when they are not independent. To get the standard deviation, we apply the square root to the variance. Now we use the null hypothesis here, we use the sample sizes here and here, and since we don't know the standard deviations in the populations, we use the standard deviations in the samples. In doing so, we must transition from the normal model to the t-model. This will be particularly important because we are working with small samples, so the t-model will be sensibly different from the normal model. There is a special formula for the degrees of freedom when working with two samples. Because the formula is very complex, when working manually, you are usually allowed to pick the smallest of both degrees of freedom. Here we would have 10, here 19, so let's use 10 degrees of freedom. The actual number with the formula is 16.32. I wrote this part in green because it is built on the basis of the null hypothesis. Therefore, it's also hypothetical. The matter of fact is that when we picked our sample, we saw a difference of 6.8 minus 7.5 equals negative 0.7 hours. The question is, what's the probability that the difference between two sample means like this is negative 0.7 or less than negative 0.7 if it is true that the difference between the population means is 0? Since we are using a t-model, we must translate this question to a t-stat. What's the probability that a t-stat is less than or equal to negative 1.69 if we work with 10 degrees of freedom? A t-calculator or a t-table will tell you that this is 0.061. Remember that the t-stat is defined as the observed value minus the hypothesized value all over the standard error. Negative 0.7 minus 0 all over 0.414 equals negative 1.69. Since this p-value is greater than 0.05, the common significance level, this study does not provide sufficient evidence that employees who occupy directive positions sleep on average fewer hours than those in regular positions. The negative difference of 0.7 hours observed in the sample is not statistically significant. P-value 0.061. If you put this hypothesis and this summary in a t-testing calculator, you will get a p-value of 0.0549, pretty close to what we got manually with the degrees of freedom approximated as 10. Interestingly, if here we used a normal model, what is commonly called a C-test, we would get a p-value below the common significance level, and then we would get the opposite conclusion. Remember that some statisticians disapprove on the use of significant levels as a threshold because the conclusions can change so much with a minor change in the sample or even in the calculations. Letter B. Complement the test with a 95% confidence interval. We have already calculated the standard error. It is 0.414. For 95% confidence, we need a margin of error of 2.23 standard errors. This multiplier is sensibly different from that in the normal model, which would be approximately 2, because here we are working with only 10 degrees of freedom, so the t-distribution is sensibly different from the normal. You can get this multiplier with a t-table or with a t-calculator. It is 2.23 because for any variable or statistic t that follows a t-distribution with 10 degrees of freedom, the probability that t is between negative 2.23 and 2.23 is 0.95. This gives a margin of error of 0.923. We added to and subtracted from the difference observed in the sample to get an interval from negative 1.62 to 0.22. Here the interpretation. We are 95% confident that the difference in the average number of hours of sleep a day between employees in directive positions and employees in regular positions is between negative 1.62 hours and 0.22 hours. This interval leaves room for the three possibilities. Employees in directive positions, on average, sleep fewer hours than, more hours than, or as many hours as those employees in regular positions. The interval captures the zero. In exercise 3, we worked with samples that were independent. Let's see what to do if they are dependent. We want to test if a diet to lose weight is effective. We have the weights of 20 men before and after using the diet. Obviously, these two samples are not independent. This weight is tied to this other weight because both belong to the same man. We say that these two samples are paired. And the way of working with paired samples is simple. You forget about the original values and you work exclusively with the differences. We will do the math for this variable d, difference. And the sample size will be 20 because the variable D was evaluated in 20 individuals. Letter A. Is there a significant decrease in weight after 6 months following the diet? The samples are small, 20, so we can use the normal or the t-models only if the population distribution of weights is normal. Let's work as if it was. The two samples are not independent, they are paired samples, so we work with the variable difference. The null hypothesis is the equality. The mean weight after the diet equals the mean weight before the diet. The alternative hypothesis is the inequality. The mean after the diet is less than the mean before. We express this hypothesis in terms of the difference. The mean of the difference equals 0, and the mean of the difference is less than 0. The sampling distribution of sample means for the difference should follow a normal model whose mean is the 0 per our null hypothesis, and whose standard error will be the population standard deviation of the difference over the square root of the sample size. As usually, since we don't know the population standard deviation, we use the sample standard deviation instead. In doing so, we transition to the t-model. By the way, this notation with the n crossed out is not official. I use it here because I think it helps students understand when and why we use the t-model. The standard deviation of all these values is 9.76 and the mean is negative 11.85. This means that our sample has a t-stat of negative 5.44. This t-stat helps us measure the compatibility of the sample with the mathematical model based in the null hypothesis. This is a massive t-stat, so this is very suspicious. What's the probability of observing an average difference of negative 11.85 or less than negative 11.85 if the average difference in the population is 0? In other words, what's the probability of a t-stat less than or equal to negative 5.44 if we work with 19 degrees of freedom? A software or a table will tell you that this probability is 0.000015. Conclusion: this study provides very strong evidence that men's average weight after 6 months following the diet is smaller than it was before. The average decrease of 11.85 pounds observed in the sample is statistically significant. P-value less than 0.0001. When the p-value is so small, it's common that rather than writing down all the digits, we just say less than 1 in 1,000 or 1 in 10,000. So it is clear that men who follow this diet lose weight. But how much do they lose? Letter B. Complement your answer with a 99% confidence interval. Here I ask for 99% confidence just to make it different, so we don't work all the time with confidence level 95%. For 99% confidence in a t-model with 19 degrees of freedom, we must use 2.86 standard errors. Again, you can get this multiplier with a t-table or a t-calculator, as I explained before. This implies a margin of error of 6.23. We added to and subtracted from the observed difference to get an interval from negative 18.08 to negative 5.62. The interpretation is: we are 99% confident that on average men lose between 5.62 and 18.08 pounds after 6 months following the diet.